Thank you very much. I'm going to try and tell you a story. The first item is totally trivial. If you look at the bottom right of the screen, it's not true. I don't have 26 slides. I used a different PowerPoint file to build up this one, and I forgot to correct that. So I'm going to try and tell you a story which I witnessed quite closely about a very promising young physicist named Hendrickson, Jan Hendrickson. So who is Jan Hendrickson? Well, he was born in Germany in 1970. In 1997, he was awarded the PhD in physics from the University of Constance in Germany. Beautiful place on on the Bodensee or Lake Constance, border between Germany and Switzerland. And later that year, he accepted a postdoctoral position with a very prominent, very distinguished physicist named Bertram Batlogg at Bell Laboratories. Who here, please raise your hand if you have heard of Bell Laboratories. No, oh, one person raised his hand. Please again, who has heard of Bell Laboratories? Another person. 2, 3, 4, okay. No, I'm actually not surprised. Who has heard of Harvard? Of course. Back in between 1960 and the year 2000, Bell Labs was just as famous as Harvard. Almost. Pretty much the same. Harvard, MIT, Bell Labs, Princeton, etc. Why? What's Bell Laboratories? So that's a very fascinating story by itself, and I will spend a couple of minutes on it. Bell Laboratories, in its heyday, was probably the largest research and development center in physical and engineering sciences in the world. Civilian, as opposed to military. There are very large military research and development centers everywhere, many countries in the world. I'm talking civilian. Probably the largest civilian research center in the physical sciences and engineering in the world. And why was it so famous and so large? Well, it had a very old history that started way back in 1925 when it was first named Bell Telephone Laboratories, and named after the inventor of the telephone, Alexander Graham Bell. And if you just skip from 1925, et cetera, there is one milestone which shines above all else. The transistor, without which we would not have computers. Well, we would have very primitive computers. Certainly would not have personal computers, laptops, iPads, iPhones, smartphones, anything like that. Nothing. The first transistor was actually, well, modeled on the vacuum tube, the triode, that was the first electronic component that amplified a signal, built on vacuum tubes. But in 1947, Bardeen, Shockley, and Breton, shown here, invented the transistor, which was a small chip, a small crystal of silicon that had a very certain structure, where they demonstrated that this little crystal could amplify a signal. And that was the birth of the transistor, December 31, 1947. And that was, of course, absolutely huge. But it wasn't only the invention of the transistor, for which Bardeen, Shockley, and Breton were awarded the Nobel Prize in 1956. Development of radio astronomy, the laser, the photovoltaic or solar cell, charged coupled devices, the cameras in your smartphone. They use a very, very dense array of charged coupled devices, or CCDs. Information theory, the Unix operating system, programming languages like C, C++, etc. These were all invented at Bell Labs, Bell Laboratories. Work done over the years at Bell Laboratories was recognized by 9 Nobel Prizes. So Bell Labs was really the center, or certainly one of the centers of science and engineering in the world. If you completed your PhD and you were offered a postdoc at Bell Labs, almost certainly you went there. So Shön joined Bertram Batlogg in late 1997. And between 1997 and 2002, he published about 120 papers and co-authored patents, many of them groundbreaking. And many or most of these dealt with properties of organic semiconductors, materials, and devices. And when I say organic semiconductors, that more or less means pi conjugated materials. Who here has had at least a little bit of organic chemistry? In school? Yeah, including in high school. Okay, not bad. So hopefully you've learned a tiny bit at least about pi conjugated materials, materials with double carbon-carbon bonds. That's a synonym for an organic semiconductor. Almost all organic semiconductors are simply pi conjugated materials. And so the first polymer, pi conjugated polymer LED, was demonstrated, reported in 1990. And even before that, the first organic LED, or OLED, was reported by a group at Kodak in 1987. And maybe some of you has seen an OLED TV in a store. Who's seen an OLED TV in a store? Okay, quite a number. So these are organic light-emitting diodes. They are based on organic semiconductors, pi-conjugated molecules. If you have one of the newer iPhones, these have OLED displays. If you have a Galaxy smartphone, these have OLED displays. Some of the Galaxy tablets have OLED displays. We've come a long way in studying and developing organic semiconductor materials and devices, and that's the proof here. Well, one of the first challenges, or one of the big challenges about 20 years ago in studying and developing organic semiconductor materials and devices was to see if we could go from an organic LED to an organic diode laser, or what's called an organic injection laser. So Hendrik Shön at Bell Labs, among other things that he did, was to demonstrate a solid-state organic injection or diode laser, or so we thought. And he had some figures here in this paper from July 2000, published in Science, to demonstrate the properties of this tetrazine-based organic injection laser. And see, for example, this shows the spectrum of the device as he cranked up the current density flowing through the device. First, you see that at 5 amps per centimeter square, the spectrum is quite broad, and as you increase the current density more and more and more, the spectrum gets narrower and narrower, and here at 150 amps per centimeter square, it's very, very narrow. It's really laser-like, because it was laser-like, or so we thought. And also, if you see the optical power output versus the current density, it starts with some certain slope, and then the slope shoots up. You get what we call gain, which is one of the hallmarks of a laser. So this was very exciting. And with everything else, and I'll show you some selection of breakthrough research that they published, he was considered to be on a fast track to a Nobel Prize. I mean, he was born in 1970. This is 2000. He was 30 years old. So I actually happened to attend this international conference on the science and technology of synthetic metals, which was really about pi-conjugated polymer materials and devices in Austria in July 2000. And Bertram Batlogg, who was his supervisor, gave a plenary lecture, and he was describing all this wonderful research that Hendrickson was doing. And it's like pulling one rabbit out of the hat after another. And finally, towards the end of his lecture, he said, oh, by the way, we have demonstrated an organic injection laser. Just like this. Wow. And many of us, including myself, came out of that lecture. We were dazed. This group, they've done everything. There's nothing left for us to do. It's like the old joke about one caveman saying to another, I want to invent something, but everything's been done. So after that, we had a lunch break, and I was talking to Anand Balapur, who was an outstanding optics guy, optical physicist, and we had known each other for a while. And we were chatting, and I was saying and Anand was the one who actually taught Hendrickson the optics that Hendrickson needed to know to do that work. And Anand was telling me during the lunch break, Joe, it's a whole new way of doing science. And I'm not sure he'd be very happy to, if I were to remind him about that, but he's fine. He's a very distinguished professor at University of Texas in Austin, but it was one of those, you don't know the meaning, sometimes you don't know the meaning of what you're saying. Why? Well, besides the organic injection laser, among other things that Shön reported between 1998 and 2001 were very remarkable field effect transistors, which are the actual building blocks of virtually every electronic device you see around you, and including a single molecule switch, like making a transistor out of a single molecule. Lasers, Josephson junctions, that's something, Josephson junctions actually lie at the heart of the new quantum computers that use qubits. They're at the heart of qubits. Superconductors made of simple pi-conjugated molecules like pentacene and parylene that you see here. And so if you're interested in this, there's also another presentation or a short summary of a presentation that was given by Bernard Feldman about teaching scientific ethics using the example of Hendrickson. But before we get to that, let's actually take a look at the selection of breakthrough papers that Hendrickson published with his group at Bell Labs, this period from 1998 to 2001. So there's one paper here, for example, electrical properties of single crystals of rigid rod-like conjugated molecules. Physical Review in 1998. A letter to Nature, efficient organic photovoltaic diodes based on doped pentacene. Another paper in Nature, July 2000, superconductivity in molecular crystals induced by charge injection. Another one in October 2000, superconductivity at 52 Kelvin in hole-doped C60. Gate-induced superconductivity, all of these in Nature. Gate-induced superconductivity in a solution-processed organic polymer film, January 2001. August 2001, another one. October 2001, another one in August 2001. Now, I don't expect many of you to realize what this means, but Nature is one of the most prestigious, prominent scientific journals we have in the world. And most scientists are lucky to get a paper into Nature once every 10 years. And Jan Hendrickson, he got 7 papers into Nature within less than 2 years. And besides those 7 papers in Nature, he got a whole bunch of papers into Science, the journal Science, which is just as prestigious and prominent as Nature. And he got 7 papers into Nature, he got 8 papers into Science in the same period, 1999 to 2001. Ambipolar pentacene field effect transistors and inverters, February 2000. Superconducting field effect switch, April 2000. Fractional quantum Hall effect in organic molecular semiconductors, June 2000. And the one I mentioned, an organic solid-state injection laser, July 2000. A light-emitting field effect transistor, November 2000. Josephson junctions with tunable weak links, April 2001. And on and on and on. And so the community was bewildered. This is absolutely amazing. It's like somebody had said he was opening a new breakthrough, a new direction in science every couple of months. And there was essentially no skepticism, no doubts. With one exception that I'll mention. Not sure I'll get to it. I may mention. But then, at the American Physical Society March meeting, this is probably the largest annual physics meeting in the world, the March meeting of the American Physical Society. It's largely condensed matter physics and other related material physics. About 6,000 to 7,000 participants every year. And so in March 2002, and I had a very, very good friend, a very distinguished physicist at the University of Utah, Zev Valley Vardani, and we would meet every year at the March meeting and discuss various things. We collaborated extensively over many years and interacted almost on a weekly basis. And this is, you know, Joe, no one can reproduce his results. And then he adds, I received samples from Christian Clock. Christian Clock? Who's Christian Clock? Well, let's go back. Here, Christian Clock. Here, Christian clock. Here, Christian clock. Here, Christian clock. 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 Not here. Well, that's okay, not everywhere, but here, and here, and here. Who's Christian clock? Christian clock made the materials, the samples that Jan Hendrickson used to do his work. So he was the materials guy. And do I actually have a picture of Christian clock? I thought I did. I'm pretty sure I do. I did. What happened to it? What happened to it? Forgive me. Oh, here it is. Right there. There's Hendrickson. There's Christian clock. There's Bertram Batlogg. Also, 2 additional pictures of Bertram Batlogg. And so Christian clock was making all of these fantastic samples for Hendrickson to measure and evaluate and interpret and analyze. So everybody wanted samples from Christian clock. And Vardany, like I mentioned, was a very distinguished physicist, and so a lot of people were very interested in collaborating with Vardany, and so Christian clock, sure, eagerly sent him samples. He says, I received these samples, and they're full of defects, no better than than other samples that I've received. What is going on? And then, in April and May 2002, all hell broke loose. Lydia Zahn, who was, I think she was an assistant professor at Princeton at the time, like many others, were furiously trying to reproduce Schoen's results and go beyond them. Well, if you want to go beyond something, first you want to make sure you're getting what you're supposed to get according to the literature, and she couldn't. And then she noticed something. A figure in the Nature paper on the molecular layer switch. This figure appeared in another paper in Science that was just published on a very different device. Ooh. And shortly afterwards, Paul McEwen of Cornell noticed something even more troubling. He saw not only duplication of figures in other papers, the same figure appearing in as described, showing results on different devices. What was the most troubling was that the noise was the same. Behavior of different devices, if they're similar, the behavior can be very similar, almost indistinguishable. But the noise, these are the statistical fluctuations or the uncertainties in the measurements, the scattering of data points around the line that you draw. All these little peaks and wiggles and supposed to be random, but if you compare here and here and here, they are the same. Now, that's a hallmark of cheating. So, as soon as Paul McEwen noticed that, he reported it to Bell Laboratories, and Bell Laboratories was a division of Lucent Technologies at the time, so the parent company, Lucent, immediately established a committee headed by a very prominent physicist from Stanford, Mac Beasley. And in September, the committee released its report. And the bottom line was extensive fraud. Of course, Hendrickson was promptly fired. And the committee, of course, detailed which actual papers they found misconduct. But the damage had been done. A lot of people had spent a lot of time and effort and money to try and reproduce those results of Hendrickson. So I work closely with my wife. We've been working together on our joint projects for 20 years or so, 15 to 20 years. And so when the whole thing broke, we were scratching our heads. You say you have demonstrated an organic injection laser. You just reported it in a paper in Science. You reported it, and I'm your boss. I never saw the laser? Or Anand Dodabalapur, who had coached Hendrickson about lasers, did he never see the laser? How could that be? So actually, around the same time, right after my wife and I discussed this, I called Anand, was, like I mentioned, at that point, already a professor at UT Austin, University of Texas in Austin. So I asked Anand, how could that be? Did you actually see the laser? And Anand just said, you could hear through the phone that he was actually dazed himself. Could not believe what was happening. I tutored him so thoroughly, every day, long hours. He knew almost no optics when he came. And I taught him all of that optics that he needed to know to do this work. I cannot believe he invented all of it. But did I see the laser? No, I did not see the laser. You see, Hendrick worked alone at night. What about those data files, the raw data that he measured? Well, I didn't even put that in the PowerPoint because it was such a lame excuse. But in his defense, Hendrick stated, I had to delete those files, the raw data files, because there was not enough memory on my computers. This was 1999, 2000, 2001. Memory sticks had not yet been invented. But still, there were already computers with enough memory. So, the aftermath. Well, after Hendrickson was fired, he went back to Germany. In June 2004, the University of Constance revoked his PhD degree due to, quote, dishonorable conduct. The physics department spokesperson at the University of Constance called the affair the biggest fraud in physics in the past 50 years. Now, Schön sued to have his degree restored, but he actually lost the final legal battle after several rounds at various levels of the courts in 2014. So we're pretty confident that much of his PhD was fabricated, a fraud as well. And I'll come back to that. Bertram Batlogg, his supervisor, who many people think should be the focus of this affair almost as much as Hendrickson himself. Well, even if you do not forgive, you can understand he was basically the director of all solid-state research at Bell Laboratories at the time. It's not surprising he didn't really have time to scrutinize the work of his postdoc as carefully as he should. And besides, he had other very competent, very successful physicists working with Hendrickson who could scrutinize, such as Anand Dodabalapur, such as Christian Klock, such as Zhenan Bao. And Zhenan Bao today is a very prominent professor, I think, of material science at Stanford. And very fortunately for Bertrand Batlogg, he became a professor at the Etika, at the Technical School of Zurich. It's a very famous institution, one of the most prominent in Switzerland. Etika is where Einstein studied as an undergraduate. So he became a professor at the Etika in Zurich in 2000, before the scandal broke, and he retired in 2016. And as I mentioned already, Anand Dodaballapur became a professor at UT Austin before the scandal broke. And he's been doing fine. Christian Clark remained at Bell Labs, but afterwards became a professor of material science at Nanyang Technical University in Singapore, and according to Wikipedia, he's also retired. So the question is, what do we glean from all of this? But before I pose this question, and I want to hear what you think, I want to mention another very prominent case that happened before Hendrickson, and that was something called cold fusion. I imagine most of you know the way that energy is produced in stars. Thermonuclear fusion. 2 deuterium nuclei give you a helium nucleus, or 4 protons end up giving you a helium. Not so simple. Required temperatures such as you find in the interior of stars, millions of degrees Kelvin, etc. Well, in 1989, Stanley Pons and Martin Fleischmann, both in the chemistry department of the University of Utah, both very well-reputed electrochemists, claimed to discover cold fusion. Hydrogen or deuterium nuclei fusing to helium nuclei at ambient temperature, at room temperature. Sounds crazy. Sounds fantastic. The end to all the issues of the ultimate energy source for the world. Last enough water in the world, enough hydrogen, to last God knows how many times the Earth will last or the sun will last. Huge, but wrong. So this was exposed very quickly. And unlike Hendrickson, this was not a matter of fraud. Well, of course, the whole affair had its culprits: Pons, Fleischmann, University of Utah president who got involved and, as far as I know, was applying very heavy pressure, along with other senior administrators of the University of Utah. Quickly patent the invention, arrange a press conference to announce to the world about what Pons and Fleischmann had invented. Don't wait for peer-reviewed articles to be published. But what you could say by just looking at the case, that these two cases, Schön and his organic semiconductor devices, and Pons and Fleischmann with their cold fusion, the first big lesson, and that's, I guess, comforting in a way, the greater the potential impact, the faster the exposure of the fraud or wrong work. And of course, this makes perfect sense. The greater the potential impact, the more other people get interested, the more other people try to reproduce, to go beyond. So the faster the whole thing blows up, gets exposed, the truth comes out. And this, of course, raises the question. So Schön might have gotten away if the work was not breakthrough. And here I want to know what you think. Actually, I have already an answer, and I think it's a pretty clear answer, but I want to see if anybody here picked up on it. So, no volunteers?
Yes.
Please.
I think he would have gotten.
You're absolutely, I think you're right. And why do you think so?
Because nobody doesn't care about work if it's not breakthrough.
I wouldn't say nobody. A lot of us do work that is not that fantastic and still.
I mean,
No, you're absolutely right. Yeah, you're absolutely right. But actually, we kind of have a proof of this claim that he probably wouldn't have gotten away with it. What's the proof? It's right there in what I described. Nobody noticed or cared that his PhD was apparently a fraud until the work at Bell Labs was shown to be a fraud. The work at Bell Labs was shown to be a fraud in 2002. But only after that did the University of Constance say, let's go back and look at his PhD. So if Hendrickson, instead of going to Bell Labs, had gone to work for some company as an engineer or physicist or just done, quote, regular work, not so fantastic, or good, solid scientific work, even if it was fraudulent, but not more than that, he probably would have gotten away with it, or at least for a while. Or maybe even a very long while. So, what do you take away from that? How do we protect ourselves from fraud? See, in both of these cases, the Hendrickson scandal, the cold fusion, well, there I'm not sure it should be called a scandal, because Pons and Fleischmann, they did not commit a fraud. They were just careless and they did not follow the rigors of scientific accuracy, of being skeptical, of doing everything you can to check and double check. The very basis of what experimental science is, to try and prove that you're wrong. What you do to try and prove that you're wrong. So if you can't, then you are probably right. And that's the closest we can come to an actual experimental proof.
Can you make a question?
Yes, please.
For example, you make some experiments and you have like unregular results. And you start to find an answer why is it matter. And for example, you have found something that is wrong. Like for example, my laboratory was not so good for this experiment. And then you like say that the result is wrong, but in reality it was like a new rule of nature. But you thought that it's. Can you hear me?
I heard you, but I guess for the record you need to repeat yourself.
Okay, I will repeat. I was asking if, for example, you make an experiment and you have like unusual result of this experiment. You start to find some reasons why this experiment not usual yet. Thank you. And for example, you can find an answer why does it matter, but in reality it was a new rule of nature, but you thought that it's just a mistake.
Outstanding question. Thank you so much. And usually when somebody tells you that's an outstanding question, that means that that person doesn't have a simple answer or no answer at all. But no, I have an answer, but it's not a simple answer. The funny thing about your question, it's an excellent question, is that you're right. That's the answer. Because there is no real hard rule about this. As a matter of fact, in my own group, we thought we had found a method to demonstrate an organic injection laser, and that was about 10 years ago. But we were very skeptical, we were sufficiently careful, and we had to make sure that everything fit the bill. So we got what we call very spectrally narrowed emission from some of our OLEDs, what we call a spectrally narrowed edge emission from the OLEDs, not forward emission, but edge emission. And it had so many of the hallmarks of lasing behavior. But it wasn't, because there was no clear evidence of optical gain. So we actually published this paper that all of these things fit like, looks like a laser. But in the end, the very last paragraph we wrote, it isn't, because there's no evidence for optical gain. But at the same time, if it had turned out later that we actually had observed lasing, that means that we would have missed the big prize. That we saw something and failed to recognize it for what it was, because maybe we did not have enough courage. That's also possible. All of these things are possible. They're not only possible, but there are examples for almost every case you can think of. But that still does not absolve us from the absolute requirement of checking everything the way that we can to make sure it fits our hypothesis, and to be brutally honest about it. As one of my colleagues just remarked this morning, you know, with cold fusion, Pons and Fleischmann, they were not dishonest. They were just sloppy, and they started to believe they had cold fusion, and then after that, everything they did, they tried to interpret in terms of cold fusion. It's like they were deceiving themselves. But I know it sounds perhaps a bit funny, but it's as if they were deceiving themselves honestly. I know that sounds like a contradiction in terms, but I think they actually believed that they had demonstrated cold fusion. So in that respect, actually, the case of cold fusion is perhaps even more interesting, challenging, and intellectually stimulating than the case of Hendrickson. Case of Hendrickson is just a case of a classic fraud where the system failed to expose that fraud as quickly as it should have. And so too many people lost too much time, wasted too much effort and too much money until the fraud was finally exposed. But this actually, the comparison between the Schön scandal and the cold fusion scandal, if you want to call it a scandal, actually brings us to what I believe is the foundation of science, which is seeking the truth. You can always make a mistake. We're humans. We make mistakes. But the essence of science, seeking the truth, exposes those mistakes. But then, the question, the fundamental question is, were the mistakes honest mistakes? So therefore, that's why I think cold fusion is actually more interesting for ethics, because that's a case that's right on the borderline between fraud and honesty. It was bad but careless research, and starting to believe what you want to believe. I think I saw perhaps, I think this is a good point to see what you think.
So may I ask one question as well? Or another science thinks that it's not true, or that how people should to protect his ideas or something this.
Yeah, again, an excellent question, because there is no simple answer. And, you know, a colleague of mine at the Ames Laboratory, a veteran colleague at the Ames Laboratory in the physics department at Iowa State University, while we were thinking, hey, have we just demonstrated an organic injection laser when we saw this very, very strong spectrally narrowed emission? And he says, you know, Joe, remember, there is nothing that resembles a breakthrough as much as a mistake. So the rule, again, is you have to be your own most critical judge about what you do. It's better that you find your mistakes rather than wait for others to do that. But at the same time, there are cases where people stumbled or may have stumbled on an amazing discovery and failed to recognize it for what it was, either because they simply failed to recognize, they just didn't see it, or because they actually saw it, but they were timid, shy, did not have enough courage to tell the world, hey, here is what it is. And I'll give you two examples of that. In 1986, Bedners and Müller at IBM Research near Zurich in Switzerland, a wonderful research lab. They were doing measurements on ternary and quaternary oxide compounds, rare earth copper oxides. And they thought they saw signs of what looked like superconductivity at 40 degrees Kelvin. This is 1986. Until then, so many groups working on superconductivity were trying to find materials with higher and higher superconducting temperatures. But until then, the highest temperature where superconductivity was found was in compounds like, niobium-3 tin, I think. where the superconducting transition temperature was 23 Kelvin. And that record stood there for quite a number of years. People were starting to think that superconductivity at higher temperatures cannot exist, higher than 23 Kelvin. Interest in superconductivity was going down. And then Bednorz and Mueller thought they saw signs of something like that at 40 Kelvin. In an oxide, no less. You know, oxides are usually, well, if they're not very insulating, they're semiconducting. Typically, they're insulators. Superconductivity in an insulator? Well, they were very careful. So they wrote a paper, and in the title was The Possibility of Superconductivity at 40 Kelvin and blah, blah, blah. And I think, I'm not sure, but I think they tried to publish it in a pretty prominent journal, but it was not accepted. And they ended up publishing it in a solid journal, but not that prominent, a veteran solid journal called Applied Physics A. And there it appeared sometime, I think, in August 1986 or something like that. And then a group in Japan decided, let's look at that. So they took a little more time, did things a little more thoroughly, maybe a larger collection of materials, maybe a greater effort to identify the actual phase that was exhibiting this phenomenon. And, whoa, they actually found superconductivity and even higher temperature. And then a third group at the university, I think it was the University of Houston in Texas, a group headed by, I think it was Paul Chu. They did even more careful work and more intense. And they actually demonstrated superconductivity at a temperature above 77 Kelvin. What's special about 77 Kelvin? Anybody? Come on. What's special about 77 Kelvin? Why do I say 77 Kelvin? Not 78, not 80, not 75.
Maybe it's temperature when some material becomes
Yes. Which material? Very, very common material.
hydrogen, maybe.
What's the most common material in the atmosphere? Nitrogen. Yes, nitrogen, well, if you lower the temperature, or if you go from above to below, nitrogen liquefies at 77 Kelvin. So liquid nitrogen is a very common phase. No, you don't find it around you naturally, but nitrogen was liquefied many, many years ago. So this was an incredible breakthrough to demonstrate a superconducting material at a temperature above liquid nitrogen, temperature above which liquid nitrogen boils. So this, and how did the group at University of Houston demonstrate superconductivity at 77 Kelvin? Not by showing that the resistance is zero, but actually by demonstrating a phenomenon that is more basic, even more basic to a superconductor than zero resistivity. And that is the phenomenon of the expulsion of the magnetic field from within a superconductor. What happens is that a superconducting material in its superconducting state, when it's exposed to a magnetic field, it will develop inside what we call our superconducting currents that cancel the applied magnetic field. So within the material, in the superconducting state, the magnetic field is zero. And that effect is called the Meissner effect. and it's very closely related to the phenomenon of zero resistivity. And if you want to demonstrate this Meissner effect, you can demonstrate it with what we call magnetic levitation. So if you have a magnet, and above that you put a sample that is in the superconducting state, then it'll develop, because of the superconducting currents that cancel the magnetic field inside, there will be a repulsive force between the superconducting sample and the magnet, and it will levitate. It will float above the magnet. This is how the maglev, the magnetically levitating train that runs between the downtown Shanghai and Shanghai Airport, that's how it runs, by this kind of magnetic levitation. Well, the group at the University of Houston, they actually showed that this sample made of material which they purified the phase that was responsible, they actually demonstrated it like that. Well, after that, all hell broke loose. And in September, October 1987, Bednarz and Mueller from IBM were awarded the Nobel Prize in Physics for the discovery of high-temperature superconductivity. That's the way to go. Yes, please.
May I ask you a question?
Mm-hmm.
Look, science is not politics or economics. Like, it's not a thing where you can hide something. Actually, if you do something, if person does better researches or fabricate researches in science, it will be seen anyway. So what's just the point of our conversation? Like, it will be seen. Like, if somebody fabricate anything, like...
Another excellent question. Thank you. And you could say you're right. Who needs to discuss this? I mean, by its very essence, science quickly exposes the fraud or the careless work. You're right. In that sense, science is the perfect self-healing discipline. But it's still not perfect, because you do witness these cases of this Schön scandal, of cold fusion, I'll give you another case where it took a long time to actually reach the final real verdict. I have a good friend from Israel who's also at Iowa State University. His name is Daniel Shechtman. And in the early 1980s, he got his PhD from the Technion, and then he was a postdoc with the U.S. Air Force at Wright-Patterson Air Force Base in Dayton. And then he got another position with what was then called the National Bureau of Standards near Washington. Now it's called NIST. Then it was National Bureau of Standards, or NBS. Now it's NIST, National Institute of Standards and Technology, or something like that. And while working, and then he went back to the Technion in Israel, and then he was on a sabbatical, or he had an additional position at NBS, and he was working at NBS, and he was doing electron microscopy, or some kind of electron microscopy, and he was looking at X-ray or electron microscopy images of crystal structures. And he saw something that he knew could not exist. A material with a crystal structure that indicated what we call a five-fold symmetry. Symmetry like a pentagon, as opposed to a four-fold symmetry, which is a square, a three-fold symmetry, which is an equilateral triangle, a six-fold symmetry, which is a hexagon. The patterns he saw in his crystal structures looked like they had a 5-fold symmetry, but all textbooks in solid-state physics stated very emphatically a crystal with 5-fold symmetry cannot exist. And the reason was very simple. If you take a 2-dimensional pattern with 5-fold symmetry, you cannot fill up the space with that kind of arrangement. So, very simple proof. Something like that cannot exist. And yet, there it was. So what did Danny Shechtman do? Did he just bury his results? Well, of course he didn't, because if he had buried his results, I couldn't be telling you about them. He published it. And he got together with some theorists to try and develop a theory that could explain that. And they succeeded. And they published a paper in Physical Review Letters, one of the most prominent journals in physics. And the title of the paper was not 5-fold symmetry, it was icosahedral symmetry, but icosahedral symmetry is the 3-dimensional analog of what 5-fold symmetry is in 2 dimensions. And who attacked this paper than no other but Linus Pauling, 2-time Nobel Prize winner. And said, this is nonsense. And Danny Shechtman and his co-authors, they called these materials quasi crystals, because it's a very weird crystalline structure, because it does not have what we call translational symmetry. It cannot, because it's not an actual periodic pattern. It does not actually repeat itself, but it has very clear order. So what is it? If it's not amorphous and it's not a crystal, what is it? So they called it quasi crystals. And so Linus Pauling comes out with the attack. These are not quasi crystals. This is quasi science. And so this feud between Shechtman and Pauling continued basically until Linus Pauling died. At that point, though, the science community had long since laid down its verdict that actually Shechtman was right and Pauling was wrong, because other quasi-crystals and lots of other patterns, crystalline patterns, like the one Danny observed, were reported in many publications. And a lot of measurements were made on these materials. And the whole field of quasi-crystals had grown sufficiently that it was totally obvious that Shechtman was right and Pauling was wrong. But it took a lot of courage on the part of Shechtman to come out and claim what he claimed. That was perhaps the overarching characteristic on the part of Shechtman in his work, the courage it took to do what he did, to come out with it, to not bury it. So that's why you could say, why are we having this discussion? It's all so trivial. Science is so perfectly self-healing. Well, yes and no. Perhaps the reason it's not so obvious and not so trivial is because science is done by humans, not by God. Now, this is a wonderful question you're asking. Please go on. There's someone with it. Wait, the microphone has to reach you.
Sir, hello. I want to ask a question. This is all the things that you say to us
is that we need to skeptical for every invention that we meet. But you say that his invention from Son, it's getting thrown to Nature Science Journal. It's the most trusted journal site that you say. I think all these things that you say, the problem is the journal site, the most trusted journal site that you say. We must regulate. It's not the scientists that the frauding all things. It just deregulates how the journal science works, and I think that's the problem. It's not the scientist the problem. I think because the scientist maybe he just mistakenly taking the method or just be frauding. That's all. Thank you.
Another absolutely gorgeous comment. Thank you. Beautiful. And I have several responses to this comment. Yes, you're absolutely right. That was part of the problem that those papers were published of Hendrickson in Science and Nature. And you could see such a rapid succession of paper in Science and paper in Nature and another in Nature and another in Science, etc. And there were rumors that the competition between Science and Nature, who would publish Schoen's next paper, was getting so out of hand that they were actually competing over who would publish Schoen's next papers. So they were literally throwing caution into the wind. And that brings up your question, your comment that this has to be regulated much better. And how do we do that? Well, it's now a requirement in the United States, if you get funding for your research by either the National Science Foundation or the Department of Energy. I know these two agencies, I know that requirement specifically because I had and still have funding from these agencies. But I imagine it's all research funding agencies in the United States. I cannot imagine that's not the case for National Institutes of Health or NIH or NASA or Department of Defense funding. The first requirement you have to sign on is that all of the files with the raw data will be open to the public. So not only are you not allowed to delete them, you have to make them accessible to anyone and everyone. So the raw data files have to be there. Will that prevent another scandal in the future? Frankly, I don't think so. Especially if, again, you will have somebody who will be doing some more regular kind of research. And if that research is fraudulent, maybe that person will just invent those raw data files. So he'll have these data files, but so what? And besides, who's going to take the trouble to go over these raw data files unless it's, again, very amazing, groundbreaking, revolutionary research? So, again, you think that this issue, this subject of ethics, is trivial. Nothing is more self-healing than science. Well, I don't know. Maybe not. Maybe science is the most self-healing of all disciplines, but it's still being done by humans. Other questions, comments, please. How are we doing for time? Oh.
really important question for most part of this auditory. Well, you said what this is appeared a new research direction in a couple of months. However, each of one being more promising for young scientists field of new materials.
I'm not sure I understood the question or comment. Help me here.
My question about what do you think about more promising field of research to young scientists in new materials field?
Everything has been done already, right? No. Go home, everything has been done. No, of course not. There are several directions I could just think of right off the top of my head. One is new materials and structures for, say, neuromorphic networks. That in which the logic of the science, the train of statements, more closely mimics processes going on in the brain, in our own neural network, right up here. Now, neural networks have already been developed. The mathematical models of neural networks were already developed years ago, and actual electronic circuits that mimic the behavior of neural networks are actually, I think they're already commercially available. But the field that would take us a step closer to actual mimicking of processes that go on in the human brain, that distinguish the human brain from any machine that could ever be made. That's now, you could see new directions using the field in which I myself have been active for many years, namely organic semiconductors, organic electronics, bioelectronics. So I think that's a very promising new direction. As a matter of fact, one of my good friends, who is considerably younger than me, has done beautiful work in bioelectronics, and especially in this area of, and now going into neuromorphic systems. He was recently appointed professor at University of Cambridge. His name is George Malyaris, and he's doing a wonderful job. And no offense, and not to belittle anybody else whom I have not mentioned, but I'm just giving you an example of George Malyaris, that's all. That's one direction. Other directions. Well, they are probably related, but they are different. Another example of new materials are materials that could be used for quantum computing. Materials from which you could make qubits, quantum bits. As I mentioned, right now, all of the quantum computers out there, all of the qubits, use superconducting Josephson junctions, and by their very nature, they have to be operated at low temperatures. Can you design, synthesize, fabricate a material, a structure that could be used as a qubit at room temperature? There's a challenge. Very exciting challenge in my mind. That's a second direction. Other directions. Well, I've given you at least two now. If I think of something else, before we disperse here. Materials that would be superconducting at room temperature. There you could probably make a room temperature qubit, but from another angle. Materials that interface between the human body and electronic systems, what we call bioelectronics, materials, new materials for bioelectronics. So, at least two areas to choose from. Any other questions, comments, anything? You've raised some beautiful questions and comments.
Which researches have you ever done? Or maybe...
Well, you're asking me about my own personal history. Actually, when I was a graduate student doing my PhD, I worked on a completely different area, something called metal hydrides, metal hydrogen systems. They've drawn attention for their potential for hydrogen storage. How do you store, if you want to store hydrogen at a very high density, besides liquid hydrogen, how do you do that? Well, apparently, metal hydrogen systems, you can store hydrogen to very high densities. You can get the hydrogen easily in and out from some of them. So metal hydrides have been considered for hydrogen storage, and that's what I did my PhD research on, various properties of various metal hydrogen systems. But then I made a switch to semiconductors, and then organic semiconductors, and that's where I've been for the last 30 plus years. So my own area in organic semiconductors, my first area was something very basic scientific, issues of trying to understand processes occurring in organic semiconductors, particularly in the excited state. What helps, what hurts the luminescence of organic semiconductors? Something called quenching processes that compete with radiative decay of the excited states that we call excitons in semiconductors. So this is an area my group has been very active in for the last 15, 20 years. And we used a technique which we were the first to apply to this area called optically detected magnetic resonance. So you ask what I did, so that's one thing we did for quite a bit.
One more question. According to your lecture,
according to the lecture, there are a lot of fabricating things like of researches and bad researches, but is there a possibility that scientists can be good, like we can say that this person is a good scientist if person doesn't have any like good results? Should I repeat?
Yes, I'm not sure I understood your question.
Look, like how can you mark a good scientist? Like, is there a possibility that scientist is good if scientist doesn't have good researches? That's another classic question. Thank you for bringing it up. And again, there are no real hard rules about that. But I'll give you another famous story, okay? That kind of, I hope it answers your question. In I think it was 1971, 1972, there was a very promising young theoretical physicist, an assistant professor at Cornell. His name was Kenneth Wilson. And then he was assistant professor for several years at Cornell University, and the time came to review his case for promotion and tenure.
you know, in the United States, not getting tenure is worse than not getting tenure. It means you are being fired. And the committee, the department, the physics department at Cornell, did not know what to do with the case of Ken Wilson. There he was, this apparently brilliant young theoretical physicist. He did not have any publications. He had a preprint. A paper he had just written, but it wasn't published yet. I think it was not accepted yet, at least in physical review letters. What do you do? And the letters of recommendation, they said, this guy's a genius, but he hasn't published anything. How do we give him tenure? So the story, as far as I know, was that at the time, a very famous physicist, Hans Bethe, was on the faculty at Cornell. And he said something very simple, and he was a Nobel laureate. And he said, if you don't give Ken Wilson promotion and tenure, I'm leaving. So Cornell gave Ken Wilson the tenure, promotion and tenure. He published this paper in Physical Review Letters. And about 20 years later, he got the Nobel Prize that was first and foremost based on this paper he published. This new theory he had developed was an amazing theory to understand phase transitions, using something called renormalization group. It's some method in mathematical physics. But you ask, how do we know if the science is good or not? Well, it depends what comes out of it. What comes out of it quickly determines whether that was good science or not good or bad science, or whether it was very significant science or not so significant. So just like science is the best self-healing discipline we can think of, it is also the discipline that most quickly provides the real verdict on any work, whether it's good or bad, honest or dishonest, significant or not significant. But as far as significant or not significant is concerned, sometimes it takes many years. That's why you see for almost every question you ask or comment you ask, the simple answer does not exist. It brings me back to some very famous saying of Einstein that he said, the solution to every problem should be as simple as possible, but not simpler.
May I ask one question more?
Well, sure. I have as much time as you have, but I think we're supposed to wrap up at 12:20.
Okay, thanks a lot.
No, but please, maybe we can squeeze in one or two more. So please. Somebody, yes.
Yes, okay. Some question about a part of your biography.
A question about what?
Biography. It's biography. It's your biography.
Oh, a biographical question?
Yes.
About whom?
You.
About me?
Yes.
Okay.
The
Yes.
question is, how do you prefer the scientist way and broke some another, for example, businesses or having this or working in some company? Why do you prefer scientist way in labs or having this?
I'm not sure I understood the question really.
He wants to ask you, how did you choose to be a scientist?
Oh, again, I can only give you my own answer. Different people, they blaze their trails differently. I decided I wanted to be a scientist when I was 10 or 11 years old. My father would take me out at night and point to the stars and tell me what he knew in astronomy, which wasn't much, but it was already enough to get me all excited about astronomy, and then from astronomy to physics, etc. So that's my own story. But different people have different stories about what got them into science. I should add one comment about that, though. When my father actually would spend time with me, we'd take walks out at the night, and he'd point to the stars and he'd tell me what he knew in astronomy. What I found so fascinating was the difference, the enormous range of scales of phenomena in nature. I think so many people do not have a hard time digesting the scale, not just of the universe, not just of the Milky Way galaxy, but our own local neighborhood in the galaxy. And I think it's very hard for adults to fathom, to digest the scale we're talking about. So I actually, when I have the time, I mention it to my own students that think about it. You know, the star that's the nearest to our own solar system. If you just say 4.3 light years away, that means nothing to anyone. Yeah, I know it takes the light 4.3 years, but do you realize what that means, it takes light 4.3 years? It means that if you have a spacecraft traveling at 1% of the speed of light, it would take that spaceship 430 years, 4.3 light years, traveling at 1% of the speed of light. It would take that spaceship 430 years to get to that nearest star. You say, but that's only 1% of the speed of light. I say, do you realize how fast 1% of the speed of light is? A bullet is usually, what, a mile a second? 1% of the speed of light is nearly 2,000 miles per second. Imagine something striking the spaceship at a speed of 2,000 miles per second. Even a microscopic piece of dust would cause enormous damage to the spaceship. How do you protect your spaceship that's going to take 400 years to reach the nearest star from every speck of dust on the way? Yeah, vacuum is vacuum, but outer space is not completely empty. There are all sorts of fascinating phenomena you could think of if you start to digest the processes that could be going, the magnitude of what's there around you. So I apologize if I've given you more than you bargained for. Yes, please.
You told about the situation when one group of scientists made some researches about superconductive materials, and nobody just trusted them. But then there were another group of scientists from Japan, and as I understand, they did the same, but they had a little bit more time. And the question is, did everybody just forget about the first group of scientists, about their researches?
Not only did nobody forget, it was them who got the Nobel Prize, because the Nobel Committee immediately recognized they were the first pioneers. So the Nobel Prize was given to those two scientists at IBM Zurich who wrote this paper with the title Possibility of Superconductivity at 440 Kelvin, and published it in a not so prominent journal. But they published a very careful piece of research they had done. They were their own worst skeptics. So they behaved the way the best scientist behaves. Last question. No more questions. Oh, there is a question here.
Well, hello. You mentioned like how you got into science. It was all about stars, and I was wondering if you believe in life in space, maybe different nations, different species in space.
You were wondering what about?
Do you believe?
Oh, do I believe? No, you're raising another very interesting question, which I don't think that was what bothered you or what brought you to ask a question. What I believe is totally irrelevant for science. It's worth a lot to me what I believe, but the only value it has for science if it leads to something new in science. Otherwise, what I believe has no value for. So, do I believe there are intelligent beings out there? I don't know. I am guessing there are, but it's just my belief. I do not think that anybody else needs to believe it because I believe it. If you believe something, that it's your belief, not somebody else's. So whether or not there are intelligent beings out there, aliens, I don't know, and I don't know if we will ever know. Yes, it's a fascinating question. And of course, the more we know, the better we can assess the probability that there is or isn't an alien civilization out there. And, again, you have very famous astronomers, Carl Sagan. He's not alive anymore, but he firmly believed that the universe is, as he said, teeming with life. But it's a belief. Or certainly talk about intelligent life. What evidence do you have? It's still a fascinating subject. It doesn't mean you should not be, doing research if you have something viable to do with that, to reach an interesting, significant conclusion. By all means, absolutely. But it should be science, not a religious belief. That's it. Going, as we say, going once, going twice. Done. Thank you very much.